I'm going to do something very informal. I'll try to do it loud and clearly. I'm really going to give a little bit of a mini course surrounding molecular modeling and surrounding Spartan, with extreme emphasis on some modern techniques, in particular density functional theory, and finally with emphasis on a few things that we've been working on in the last several years, dealing with molecules that are flexible and dealing with NMR spectroscopy in particular. That may not be relevant completely to this audience, so you have to forgive me for that. Maybe 30 years ago now, we started out with a program named Spartan. The name was deliberate. It was designed to imply simplicity. The purpose of Spartan was really, and has maintained, to provide access to modern molecular modeling tools to chemists. And along that period of time, a long period of time, quite a few things have changed. In particular, the technology has changed such that what was the most difficult problem at that point, which was access to computing, has become almost irrelevant now and will continue in that direction. So I think you will see a paradigm change in chemistry, whereas modeling will be more and more used, not at the expense of experiment, but rather in support of experiment. The requirements of modeling, there are many of them, and I could put them mathematically, but I'm going to list them really only two requirements, maybe three. The first is practical. Whatever you do has to be applicable to the problems that actually you care about. If you didn't really care about that, you could try to solve the Schrödinger equation for hydrogen and be completely happy with that. But if you care about things that are more complex than that, then you have to put the word practical in there. And there's a recognition that you may not be able to do the very best technology available on the problems of interest. You may have to make some serious compromises there. So the first requirement is really that whatever you're doing has to be practical. You actually have to be able to do it. The second requirement is whatever you do has to be well documented. What that really means is that you have to have some level of confidence in what you're doing. That again requires some extensive prior work, and it also requires that maybe the methods that you're going to consider to use are restricted to a relatively few out of literally hundreds of possible choices. So we'll get into that as well. The third one is less relevant, maybe, but it's easy to use. What I mean by that is the mechanics of doing a problem should be not really very difficult and not really very intimidating. At the very extreme of that, the most difficult thing you'll have to do in setting up a problem is to, build a molecule or to draw a molecule. It shouldn't really be any harder than that. The caution here is that the difficult part of modeling is exactly the same as the difficult part of experiments. It's in trying to formulate questions. It's trying to ask the right questions and try to learn how to process the answers to those. Let me start out by giving you a very simple example of modeling, really very simple. Here's a molecule, luminol. It's a famous molecule. It exists in every organic chemistry textbook, and in 8 out of 10 times it's drawn this way. And so the question you might ask in modeling, and again I'm using this as an illustration rather than something important, is what is the structure of luminol? Is it that, or is it one of a number of tautomers that you can draw? And there are 4 more. There are actually 5 more, but for lack of space, I've eliminated one. And they're the following. So how would you approach this in a molecular modeling sense? Well, the first thing you'd do is you would draw all the possible structures, and you would subject them to something. So let's switch to Spartan, since I've been asked to do demos here as well. So let me switch here. And I'm now going to draw luminol. And I'm just going to sketch it. So here's one structure. Here's the one that I put up. Or you could say, what are the tautomers? Now I could draw them, or to make things simple, we've put in lots and lots of facilities to do things that are best done by machine. Here's one, produce the tautomers. So what I'm going to do is I'm going to produce a list. And it's going to say, here is that list. It's actually giving 6 of them. Okay, I've got 6 of them. And if I step through them, here's the one I drew originally. Here's an imine. There's another imine. And then there are 2 that have, there's one which is a dicarbonyl. And then there are 2 which are monocarbonyls. So there's 6. So I've now generated them all. So that should be the hard part. And let's compute the equilibrium structure. So I have to pick up theory. I have to pick a method. This is where people get rather intimidated, but I'm going to pick a method which is a density functional method. I'm going to talk about that quite a bit in a while. And I have to have confidence in that the method I pick is able to reproduce structure, which is what I'm asking at the moment, within experimental accuracy. And what I mean by experimental accuracy is a bit variable. It's variable depending on what quantity I'm talking about. Here I'm talking about structure, and then it's variable. Then it's depends on the source of the experimental data. Now, structures are well known for very small molecules very accurately. But the vast bulk of experimental data comes from X-ray crystallography, and there the accuracy limits or the precision limits are much, much lower. And so that really should be our standard. What we'll do is we'll get this structure, and we'll have some confidence that it's right. And then let me go back to Spartan here. Bit of thing, and I've only got 5 listed here, and I've put names. I haven't put names on them, but what you'll see here is the 5 listed. These are just the structures from quantum mechanics, and you'll see the first interesting conclusion that comes out is that one of the structures is something has happened without my having asked that question. Of the 5 structures at this very simple level of theory, I've listed their relative energies, and let's focus on the best of the bunch. And the best of the bunch is this one, which is not the one which is normally ascribed as the experimental structure. And then there are 2 that are quite close to it, and another one which is quite close to it. One of which is so you can see that rather rapidly you can get some assessment of what something looks like and how good it is. And the first conclusion that's coming out is that preliminarily, at least the structure which the theory is saying is the good one is different from the experimental one. So the conclusion that's coming out of this is that there are 3 of them that are pretty good. One of them is better than the other 2, this one. And there are 2 of them that there's one that's less good, and then there's the imine, which I didn't show you, actually rearranges. It's the one that was very high energy. If you let it actually go, it rearranges. Now, the theory here is not very good, and we have to have, again, this comes down to how well do your methods perform. And if I say, well, I have this level of confidence in a given theory, how do I do better? So the next step is to really, in an investigation, well, it's the energy. I mean, it's simply looking at the energy. One could look at the quantity that's directly calculated. Again, I'll say a little more about this later. Is energy. You can, from energy, get enthalpy. That takes a little work, or you can, with a little more work, get Gibbs energy. Usually in thinking about relative comparisons, one object relative to something similar, energy is just as good as any of the others. But in thinking about comparisons that are a little more diverse, enthalpy is usually better. Energy is, the difference between energy and enthalpy is, there are two major differences. One difference is 0 point. which is the energy of 0 point vibration, the one you can't get rid of. Now that number among similar molecules is almost, it's a big number, but among similar molecules is almost the same. The other difference, which is more subtle, is temperature. The experiment, forgetting 0 point now, the experiment refers to 0 Kelvin. As you go to real experiments, which are not performed at 0 Kelvin, there is a correction to that. I'll say a little bit about that later. Those corrections are well defined, and those two will give you enthalpy. From enthalpy, you can get heat of formation just simply by subtracting atomic contributions off. That's a trivial change. In general, if you look at subtle comparisons, entities that are similar, then energy enthalpy will be very similar to that. If you look at less subtle comparisons, that will not be the case. Again, I'll get into that a little more. What you see here is that if you go to a better theory, and again here I'm using terrible nomenclature, but if you go to a better theory, what you see is that a theory that you actually have confidence to within a few kilojoules. I'm on a campaign to push kilojoules. The Americans will never agree to that. 15 kilojoules is something like 4 kilocalories. Okay, so you can get confidence. Now, you can go one step further, and I'm going to do this, I'll do this a little bit later when I talk about NMR. You can now say I've got 4 structures. Of the 6, 2 have collapsed, actually. I've got 4 stable molecules. They're 4 tautomers. And a tautomer means it's equilibrating very rapidly. So in fact, in a normal experiment, you're only going to see one of them. So you can ask, if I look at some spectral information, and the one I'll look at is NMR, and I'll do this later. And I'll just give you a numerical way of looking at if I'm any good or not. Here is, what I'm showing here is the difference in chemical shifts between an experiment, there's only one experimental number, and the theory. And so I'm going to look at that in the 4 stable molecules. And so what I'm plotting here, it's hard to see. Let me go to a simpler model, tube model. What I'm plotting here, the numbers are the difference in chemical shifts. And as I walk through those 4, you'll see the differences here are, there's a 2 and there's a 1. If I go to another one, I have differences of 6 and 11. That one's clearly no good. If I go to one, here's another one. I have differences of 7 and 5, not very good. Here's another one. I have differences of 5. So of those 4, one of them fits really well. And a little bit later, I'm going to come back to this same example and show you a different way of measuring the same thing.